So till now we have seen one type of RNN architecture. So let me just draw what we have seen till now, right? We have xi1, right? It generates an output which is just fed into, which is refed into xi2, right? Again refed into this, so on and so forth. Finally you have your xi mi, right, which generates your yi here, yi hat to be precise, right? So this is the architecture that we have seen till now. And remember, when I just place this, what it really means is that the output here is taken and there is one more sigmoidal unit here. So just to be really clear what I'm drawing here, every box that I draw there, right, with xi and yi, what it means is that there is a w, there is a w, there is a w dash, and there is also a w double dash. So all these weights are there. So whenever I draw something like this, when I say this is xit and this is yi, right, what I mean here is that this whole structure is there internally. There are two activation functions, one to generate the output OT, and the other with a sigmoidal or with a softmax layer to generate yi. That's what I mean, right? So just to be clear that you're not missing out. So here you have your O1, O2, O3, OM, and this OM is fed into your one more layer G function, like a softmax function or a logistic function to generate yi hat. I just want that to be clear. So we've seen one example of this. This is called a many to one. This is called a many to one RNN, right? The reason being, your input is a sequence, is a sequence with multiple values, many values, but your output is only one, right? That's why it's called many to one, because your output is just one, right? So these types of examples, as we have seen, these are very useful for sentiment classification. Some of the examples of this, we have seen the sentiment classification, right, with our Amazon food reviews. That's one example. The second example is, imagine if I'm given a movie review. Imagine if I'm given a movie review and I want to predict what is the star rating. What is the star rating of this movie? Then, so in a sentiment classification, my yi is a two-class classification, positive or negative, right? In a movie review setting, again, in sentiment classification, your input is a sequence of words. Even in a movie review, your input is a sequence of words, but your output yi is basically one, it's a multi-class output, 3, 4, 5, right? You can also think of it as a regression problem with values ranging between 0 to 5. You can think of it as a multi-class problem or a regression problem, because you have only, there is no 0, there is 1, 2, 3, 4, 5 stars, right? There are 5-star rating that you can provide. So these are a couple of examples, like movie review, predicting the star rating of a movie review or predicting the sentiment of a review, right? These are problems where your input, you have multiple inputs because you have a sequence of words, right? That's why it's called many, because you have inputs one word after the other, but your output is only one. This is called a many to one RNN. We'll see other structures of RNNs, okay? So this is many to one. There is something called as one to many. So let me explain how a one to many architecture looks like. There is something called a one to many RNN. The one to many RNN looks like this. You have your RNN unit. Your input is just one data point. There is no sequence in the input. So there is no sequence in the input. In the input, there is no sequence. Like for example, this xi could be an image. This xi could be an image, right? Which is basically a matrix. You can think of it as a matrix, right? Your xi is not a sequence. It's just a single input. But your yi's, so your input is not a sequence, but your outputs, your yi, could be a sequence. That's why it's called one to many. Okay, so let me just draw the architecture here. Your yi1, this is fed to this. Then you have yi2, fed again. You have your yi3 hat, right? And so on and so forth. You have yi4 hat and so on and so forth. Right? Look at this. Look at the structure here. Your input is 1. This is 1, but your output is many. So this is called a one-to-many RNN, right? And the structure, each of these boxes are the same ones that we have seen before. Each of those boxes internally Each of those boxes internally are simple structures like this. If it's a simple RNN, right? If it's a simple RNN, each of those structures, each of these boxes is a simple RNN. Is a simple RNN, right? So this is one to many. You might wonder, where is this useful? So there is a problem called image captioning. There is a problem called image captioning. The task of image captioning is that you're given an image as an input, which is just one data point. It's not a sequence. And what you want to output is a sentence which explains what is there in the image. What is in the image? What is in the image? So for example, imagine you have an image with a person's face, right? With maybe with two faces. This is the input image, let's say. The output would be that contains two human faces, right? So this is basically a sentence. Look at this. This is actually a sentence. So your output, your yi is a sequence, right? Your yi is a sequence, or it's basically a sentence in this case. Your input is just one point. It's not a sequence. So it's called one-to-many. Image captioning is a very, very standard example for one-to-many RNNs. There is a third type of RNN called many-to-many. And there are two types of many-to-many architectures. Let's go to the simple one. Okay. Let's call this many-to-many RNN type A. Let's just call it type A. And the structure looks like this, right? You have your input. So many-to-many basically means that your input is a sequence. Your input is a sequence and your output is also a sequence. Okay. So your input here can be xi1, right? xi2, xi3, and so on and so forth, right? Your outputs, so for every input correspondingly, you have your yi1 hat, yi2 hat, yi3 hat, and so on and so forth. So this is basically a many-to-many architecture because you have many inputs, right? And you have many outputs. You have many outputs. But note that the size of your input and the size of your output is the same here. In case A, so this is a many-to-many. This is a many-to-many, same length input and same length output. So you might wonder, what are the applications of this? If you want to determine the parts of speech, for example, imagine if I input a sentence here, right? Let's say I input word 1, word 2, word 3. The output could be that this word is a verb, this word is a verb, this word is a noun, this word is a proverb, this word is an adjective, right? If your outputs is also a sequence such that for every input, corresponding to every input, there is a word. This is called parts of speech detection, right? You're given an English sentence and you're expected to find whether a word is a verb or a noun or a pronoun or a proverb or an adjective, etc. This is one example. So detecting parts of speech for a given sentence is very, very important task in natural language processing, right? So this type of architecture, it's a many-to-many RNN where the input and the output are of the same length. It's often used in NLP tasks. There is a different type of many-to-many architecture. So you can have a many-to-many RNN where the input and output are of different lengths. Let's take an example for this. A very good example for this is translation, is machine translation, where the task is to translate a sentence in English, to let's say Spanish, right? Your English sentence may contain 20 words, but your Spanish sentence may contain only 10 words because probably Spanish has better ways of representing the same sentence. You could have an English sentence which is only 10 words, but your Spanish sentence could be 20 words. Or the input and output could be of different sizes. That's the key point here, right? Now, how does the architecture here look like? So you basically have your inputs first. So first you input everything, xi1, right? xi2, right? xi3. I'll just draw a simple example. Okay. Now, suppose your input is, let's say, length 4. Okay, you have your input here, your output starts here. So your whole input is done here. This is all of your input, right? Your output can start here, which is yi1 hat. Your input is no more here, only yi2 hat, right? And yi 3 hat. So what you notice here is there is an input here and your output start after inputs. Your output start, because remember this is the time axis, right? This is the time axis. So what it's doing here is it's first taking all of the input. It first feeds in all of the input and then generates an output after feeding in all of the input. So this is also called as an encoder decoder network. Okay, so this part is called the encoder part. This is called the decoder part. These are also called sequence to sequence models, right? Because you're inputting a sequence and you're getting an output as a sequence. And this specific, remember, this is also a sequence to sequence model. This is also a sequence to sequence model because you're both many to many RNNs of same length. This is a sequence because you're sending an input which is a sequence and your output is also a sequence. Similarly, your many to many RNN which is of different lengths is also a sequence to sequence model, but it has an encoder before the decoder starts. That's the difference, right? Here, both this sequence and this sequence are being generated parallelly. But in this case, your whole sequence first is input, your input sequence is taken in, then your output starts getting generated. Because without seeing the whole English sentence, I may not be able to translate everything to Spanish. As soon as I get a word, I can't just simply translate that word because there is a grammatical structure to languages. The grammatical structure for English may be different from the grammatical structure for Spanish, right? So it's important that I first encode everything. I take all the inputs followed by all the outputs. So these are the four popular types of architectures. You have a many-to-one that we have seen in sentiment classification. We have a one-to-many like image captioning. We have a many-to-many of same length and many-to-many of different lengths. Obviously, there is one more case that I've not written here, which is one-to-one. Because you've done many-to-one, you have done many-to-many, you've done one-to-many, you've done many-to-many both types. But what about one-to-one? One-to-one is basically your MLP, right? You have your Xi and you have your Yi. There is no recurrent structure here, right? This is basically only one input and you get one output. There is no sequences, no sequence in input and output, which is your standard unit, right? This is your simple MLP type of unit, a multi-layered perceptron type of unit, right? So just for completeness, I'm just mentioning one-to-one. But the concept is simple. This is how the architecture looks like. But please remember, each of these boxes, internally, if it's a simple RNN, internally there is this whole structure. Don't forget that there are three weights. There is a weight that is taking the input to the function, to the activation function. There is another weight which is taking the output from the previous layer. There is a third weight which is generating your Yi's. So there are three sets of weights that you have to be very careful about. Because if you miss that, you'll mess it up. Okay, it sounds very good. It rhymes very well. If you miss it, you mess it up. Okay, so these are four many-to-many, one-to-one, one-to-many, and many-to-many architectures. These are very common, and we'll see lots of examples in this course. See, we'll see a lot of these examples in two cases. We'll have some simple case studies. We'll have lots of case studies where we will see LSTM being applied on real-world problems, where we'll encounter some of these cases, right, of different architectures. Also, we have some examples at the end of this chapter itself, where we'll see some of these architectures in play, right? And of course, we'll do full-fledged end-to-end case studies the way we have done with classical machine learning techniques, where we will see LSTM being applied. So we'll encounter most of these types of problems as we go forward in this course.